see there's height coming in, with a minute to spare. Some of the regulars, Tucson regulars, are gone over to the old seminar rooms. They're trying the doors and everything locked.
You need a better job. You need to be a low jack. Where in the world is Gary?
That's a great idea. A low jack my
favorite Tom Moses keys. Because he's, 5 million miles.
Yeah.
Pilots. How much are you paying these people to come?
At least $100 a piece.
It's so expensive. You're allowed to have a room that just took your money.
All right. Well, good morning. I hope you've had time to get a cup of coffee. Art, thank you very much. Appreciate it. Welcome to the final day of the 2024 American Gem Trade Association Tucson Elevated Seminar Series, sponsored by the American Gem Society. Gemology as an evolving science. Our first speaker this morning is Dr. James Shigley, Distinguished Research Fellow at the Gemological Institute of America in Carlsbad, California. Jim joined GIA in 1982. He has his doctorate in geology, is the author of numerous articles on diamonds and colored gemstones, and is a well-known speaker on the gemological circuit. Dr. Shigley's role at GIA is to help direct research activities on the identification of natural, synthetic, and treated diamonds, as well as colored gems. This morning, Jim is going to give us a brief look back at gemological research, talk about where research is today, and then where it might be heading in the future. Please give a warm welcome to Dr. James Shigley.
Thank you, Gary. I'm not certain I'm in the elevated category, but thank you for coming today and braving the weather. The talk today is, as Gary indicated, the evolving technical science of gemology. Kind of a brief look back, but maybe a look at current times and a little bit of looking forward. Well, I think the gem industry is evolving in a lot of different ways, and these are just some of the ways that are kind of more connected with the talk. Increasing natural sources of gems, certainly a wide availability of synthetic and treated gems in the market. Standard gem testing and methods and techniques can be challenging, and there's kind of an increasing reliance on gem identification reports. There's certainly growing importance of scientific instrumentation in laboratories, and there's a development of gem testing instruments for use in the trade. We certainly have the internet and social media as sources of information. I would say sources of variable reliability. And then I think really the message this morning is kind of what I see as kind of a widening knowledge gap between gemological research and the gem trade. As Gary indicated, I started in 1982. If you'd walked in the door, this is me, but it's 1990. But if you walked in the door of GIA in June of 1982 with me, there are certainly many things that have been recognizable at the Institute. We were teaching gemology, we were issuing diamond grading reports, gem identification reports. But as my good friend Emmanuel Fritsch can confirm, it was a different research world, a different scientific research world at that time. Very little scientific instrumentation, no personal computers, no email, no cell phones, no internet, social media. paper documentation of results. That means you had a worksheet which you filled out by hand, or you had a graph of a spectrum on a piece of chart paper, and you didn't have any really easy way of storing that, except in binders. And the real challenge for us at that time was there was no searchable online or computerized information database. I just wanted to kind of indicate the general areas of research at GIA. Of course, gem identification, we're interested in the conditions and environments of gem formation, natural formation. We're going to field collecting at localities around the world. Country of origin determination for colored stones, origin of color and optical phenomena in gems, gemstone cut and visual appearance, and finally testing instrument development. These are really the main areas of our research effort. I just wanted to start again with this database idea. This is the invisible part of gemological research. It's the invisible part, and it's the most, in a way, the most difficult part. It's the most time-consuming part, I guess I should say. Research requires you to have access to information on the types of gems you're going to be investigating. And by information, I mean observations, gemological properties, photographs of inclusions, spectra, chemical data. You have to have a database. There's certainly data on gems. It's widely available in the gemological literature. But that information may be difficult to access and may or may not be useful to the problems that you're working on. So what researchers have to do, especially in our field, is we have to create this type of searchable information database using oftentimes our own instrumentation, and ideally, whenever possible, characterizing gems of known origin. Known natural stones from a known locality, known treated stones where we know how they were treated, known synthetic stones where we know how they were grown. Data from samples of known origin are of the most value for this database. Now, of course, obviously, we get a lot of client stones coming into the lab for identification. We're characterizing them. It goes into the database as well, but it's then, we don't have quite the reliability of where these things come from, but nonetheless, they're of value. So this is the invisible part of research. It takes years to create this kind of database, again, using your own instrumentation and hopefully samples where you know where they're coming from. Just a quick little geology on, there's certain important crustal environments of gem formation. Sapphire in a magmatic basalt, an emerald and calcite along a hydrothermal vein where their crystals are growing from a high-temperature mineralized solution, and finally the ruby and amphibolite crystallization or recrystallization in the solid state during metamorphism. And of course, I should add that certainly opal forms in a sedimentary environment. These primary host rocks weather oftentimes, and they release the gems into secondary alluvial deposits. But the important thing is the chemical elements, which are so important for identification. The chemical elements in gem minerals arise from these geologic environments of formation. We've had a pretty extensive program over the last 14, 15 years to go to exotic places. There have been about 98 expeditions, 21 countries, collection of some 22,000 colored stone rough gem samples. This is really important for our research program. Again, having samples of known origin that we own, so we can cut them in half or grind them up, which clients don't. Clients kind of hesitate for us to destroy their gem in research. But collecting rough gems, we can have kind of a hierarchy of reliability. Ideally, we would like to dig the stone out of the ground ourselves. Second step down, we watched it being dug out of the ground. Third step down, we bought it at the mine. So there's a hierarchy of reliability, but we're also collecting information on the local geology, the host rocks, obviously the very descriptive gem coordinates where this location is, sample acquisition conditions, but also photographs and video that we can use in our course material. So this is a huge part of our research of going to faraway places. I can't say I've been on many of these. My colleagues have kind of said, don't come and touch the rocks, James. But this is really a very important part of research, gathering gems of known origin in the field. Well, you may be thinking of investing in some scientific instrumentation wherever you are to study gems. Just a few thoughts on instrumentation. There's a pretty significant purchase price, $100,000, $500,000, a lot of price for some of this modern instrumentation. And then there's a pretty hefty 10% annual service cost that keeps going on to keep the maintenance up on this equipment. You need trained operators and data analysts, and you need data collection and analysis procedures. You need to periodically calibrate your instrument so you can have confidence it's working correctly. And the next point, because we cannot modify the gems in any substantial way, we have to analyze them as they are. So it could be a gemstone, a piece of jewelry, a mineral specimen, a jade carving. You have to fit the sample in the instrument. So you need to oftentimes have to modify the sample chamber to hold the samples. And if you're trying to do a spectrum through a colored stone or diamond, cut stones are not meant to be windows, they're meant to be mirrors. So you've got to get light through the stone to the detector to record the spectrum. And finally, you've got a 5 to 10 year lifetime. Not that the instrument is going to stop working, but sometimes the software is no longer continued. So if you want to spend some money, just kind of recognize that you've got some things you've got to be aware of. I think the microscope is the most important tool for gemologists. We have a couple of microscopes here and a variety of illumination conditions. A colleague, John Puebla, who's here at the show, produced kind of a nice book on photoatlas. And then my colleague Nathan Renfro, we've been making these inclusion charts, and the most new one is on Barrel, and it's available over in the current G&G up at our booth. And of course, you well know that we're trying to capture diagnostic mineral inclusions in photomicrographs. Just a couple of examples. These inclusions are trapped from the surrounding environment before, during, after, I guess, gem formation. And they're very important for origin and country of origin and gem identification. I'd like to turn for a minute about chemistry. This is a pie chart just showing these 10 elements represent about 99.8% of the composition of the Earth's crust. So oxygen, silicon, aluminum, iron, calcium, sodium, magnesium, potassium, titanium, hydrogen, 99.8. So every other element is about 2% of the Earth's crust. Well, titanium, iron are on that list, but we have important coloring agents, vanadium, chromium, manganese, copper, cobalt, nickel, so on. And also there's some rare elements that are important for gem minerals, lithium, beryllium, boron, and so on. So this is kind of the chemical world that we're operating in, because these are the elements that are going to show up in gem minerals. So if you're going to do a chemical analysis, there are a couple of considerations. Are you going to do a qualitative analysis or a quantitative analysis? Qualitative is what elements are present. Quantitative is what elements are present and how much of each. Is this a volume or spot analysis on the material that you're analyzing? How much of the material are you analyzing to generate your chemical data? Do you need any sample preparation? And finally, is there any sample damage as a result of the analysis? I just show as an example blue sapphire. Elements in minerals, gems of all kinds kind of fall in three categories. And I think I've just tried to say major, minor, trace elements and give you some indication of relative amounts. So above 1% plus or minus is major elements, in this case aluminum and oxygen. Minor elements roughly about 0.1 to 1%, and then trace elements below 0.1%. Now, major elements are normally calculated, or the data is presented either as an atomic weight or an oxide weight. This is the historic way of, and you read old mineralogy books or current mineralogy books, and you'll see rock or mineral analyses oftentimes presented as not just iron, but iron oxide. It's just kind of the traditional way of kind of connecting up chemical data. Minor elements calculated the same way, but trace elements are often calculated as an atomic weight. Well, these minor and trace elements substitute for the major elements in the crystal structure of the mineral, but they're distributed oftentimes somewhat unevenly in the crystal structure, but it's the detection of these, especially these minor and trace elements, that is of vital importance for gem labs doing chemistry of gemstones. We've kind of changed our way that chemistry data is reported. So the major elements, as I said earlier, historically of percent iron or percent iron oxide. But as you go down, we've kind of changed to a unit called parts per million. So I've just tried to kind of compare percent on the left and parts per million on the right. So again, above 1% or 10,000 parts per million is a major element. Above 1,000 parts per million is a minor element, and below is trace elements. And we're oftentimes in kind of the trace element world. That is chemistry elements below about 1,000 parts per million in gemstones. And of course, if you can go even further. So trace elements and the ppm level is really what is important for colored stone chemistry. But we're oftentimes asked, can you tell where diamonds come from geographically? Short answer is no, we can't. They don't come from good and bad countries, they come from deep in the earth. But diamonds are such a pure mineral. The carbon atoms are in such close proximity, tightly bonded, it is very difficult to get larger trace elements in a diamond structure. So in a diamond, whereas in the colored stone chemistry world, 10,000, 1,000 ppm, but in the diamond world, you may be doing 1,000 times lower concentrations. And because we don't have diamonds from all the localities to study and all these things, there's no database. So there's no basis that I know of. You know, we've been looking and grading diamonds at the lab since 1955, issuing reports. There's certainly nothing in the diamond itself, typically, that's going to say where it's from. This is the challenge. I don't think, there may be some claims that you can tell where diamonds come geographically, but I have to say I don't really believe them. And I think one ought to take, I guess I'm saying, I don't know of any scientific study on samples of a wide range of origins that really has demonstrated you can do this for a diamond that you don't know where it's from. Well, when in the parts per million range, you know, these are getting to be very small numbers, and you may have kind of a hard time wrapping your head around what's parts per million. So I tried to come up with a little analogy. I think most of you have probably been in a big city at least once in your life. New York City here, population roughly 8 million, plus or minus. I know that's quite the population today. But 1 part per million of that 8 million is 8 people. 1 part per billion is 0.008 people. And if you want to put it in back in the blue sapphire context, if you had a piece of blue sapphire composed of 8 million atoms, most of them are going to be aluminum and oxygen, but you're chasing after 1 part per million or 8 atoms of something else. This is a real technical challenge, because if you're doing a spot analysis of this sapphire along the girdle, you're selecting places, hopefully, normally you're selecting places with no inclusions, even coloration. And you may hit this one of these 8 atoms with your analysis, and you detect it. Or you may not. But if you don't detect it, there's 2 possibilities. Either it's not there, or you analyze the wrong location. I'm just saying we're into a extreme trace element chemical analysis world that's kind of pushing the limits of what we can do scientifically in this idea of certainly colored stone origin determination. The question is, brother, I think that's one, because when that came, whatever it is, 20 years ago now, and beryllium was at very low concentrations, parts per million, and it was very effective coloring sapphire. We had to have a new technique, which I'll show you here in a second, that allows us to do quantitative analysis at very low concentrations, parts per million level, to chase after and detect the beryllium. But it's more important today for country of origin reporting. Is this a Kashmir sapphire or a Burmese sapphire or Sri Lanka sapphire? And a lot of it's based on this chemistry. If you're going to do a quantitative analysis, you really need to have a standard, something where you know the concentration of the elements in the standard. So if you're going to do calculating in an unknown, you want to compare that to the analysis of a standard of a similar material, ideally. So we've developed a set of synthetic and natural corundum standards, because a lot of our country of origin reporting is, of course, on ruby and sapphire. We had grown for us the corundum crystals, synthetic crystals shown here, with elements of interest at known concentrations that were evenly distributed in this crystal. And we analyzed it by a number of different techniques. And when we were satisfied we had a fairly uniform chemistry, we sectioned this crystal, and we provided these standards to all our lab locations that are involved in this country of origin reporting. It's kind of, you don't have a standard, it's kind of like doing diamond grading, DDZ diamond grading without the master stones. You're on the DDZ scale, colorless yellow, but unless you have standards, master stones, in this case, chemistry standards, you don't know the right analysis. There are 2 techniques that we use for chemistry. First is X-ray fluorescence. It's good for magnesium and above on the periodic table, if you remember your chemistry from recently or long ago. This is a rapid qualitative analysis of the elements that are present. So when the instrument illuminates the material with X-rays, it changes the electron configuration, and you have a fluorescent X-ray of lower energy that's being emitted. And you can detect that as these light-colored blue peaks on the graph. So this is X-ray intensity going upward and X-ray energy across the bottom. These peaks are at specific locations on the energy spectrum, and they are the fingerprint of the elements that are present. So in this case, this is probably copper tourmaline. I just circled with a red box. There are 2 peaks for manganese, but I think you should be necessary. You have to recognize that. Don't think that because the peaks are higher, there's more of an element. It's not that straightforward. But this is a rapid, qualitative, quick way, especially for detecting transition metals, color agents, and a lot of gem materials by this technique. The technique that we purchased starting to deal with the beryllium diffusion issue is laser ablation mass spectrometry. So you see in the upper picture, the laser unit is on the right, and the mass spectrometer is on the left. On the right there, you see some little 50 micron, very tiny spots. When we first kind of started testing sapphires, some of our lab clients were a little uncertain of what we were going to do to their Kashmir sapphire. So I took a couple of our sapphires from our collection, and I inscribed GIA on the girdle of the sapphire, just like we would do for a diamond. And we put the laser spot next to the inscription of the GIA. The laser spot is much smaller than the inscription, and that can be fairly easy. It's very shallow. So what this is, the laser comes on, flashing, and is burning burning down through the surface and blasting out tiny particles of the material that flow through by means of a gas into the mass spectrometer and all what goes on in there. But you end up with a graph. The operator sees the graph kind of like on the bottom. So on the bottom, this is counts on the vertical axis and time going across on the horizontal axis. So what this is, we carefully select locations on the sapphire to analyze. We normally kind of have a couple of them because we're trying to batch these in a sense, but we're going to collect about 30, 20, 30, 40 seconds of a background. That's the BKG part of the spectrum on the left. It's kind of a background level. You then turn the laser on. It's flashing. You can see it flashing on the edge of the stone. And the signal starts jumping up there on the right side. We're going to let a few seconds to let it burn through anything on the surface, and then we're going to collect the data over about a 20 or 30 second period. And from that graph, we can calculate all the elements that are present at very low concentrations. This is a quantitative spot analysis. You can detect really everything above lithium in the periodic table, naturally occurring elements, down to the parts per million range and even perhaps less. There's no sample preparation, but there is minor surface damage, and that's why I was trying to calm our clients about where we're destroying their sapphires. Well, from that, you're probably familiar with some of the articles in our journal elsewhere where you have plots of chemistry data. In this case, gallium, which is an element that substitutes quite readily for aluminum, versus vanadium. And you'd have samples of known origin represented by the various colors, and you get this kind of data plot. And you have your unknown as the black circle with a little red over red. Well, as you quickly see, as you embark down this road of chemistry, it would be nice if the plots for the sapphires from different countries would show up in different places on the graph. But that is not always the case. So you end up with a bit of data overlap. Now, what do technicians at GI do? Well, we try another couple of pair of elements. If this doesn't work, I know we do. We try a number of combinations, or plot them on a three-dimensional graph. But this is iron titanium plot. This is what I would call data chaos. Why are we having so much challenge with country of origin reporting? I think in other labs, of course. I think we're chasing smaller and smaller concentrations of elements. But also we have more and more localities producing material. And, if you're in the lab and you have a client stone, you can't just kind of arbitrarily say, there's no way this sapphire could come from this place. This place has never produced anything. That's kind of an assumption. We can't start from that. We kind of say that any of these localities is potentially possible. But this is data chaos. So one of the techniques, and I can't claim it's that original, but it's called filtering. So this is a plot of, again, sapphires, magnesium and gallium on the bottom part of the graph, and vanadium is on the vertical axis. Now we know where the unknown is, the black spot in the middle of the graph on the left, because we just measured it. But you can't see it. So what we do is we're going to mathematically remove the data points that are that get farther and farther away from where the unknown is. And when you kind of remove a little bit of the noise, the excess data, you start seeing a little more clearly where this location corresponds to. Again, you have to remember origin reports are expert opinions based on a lot of different properties and the experience of the lab management. But this is an extremely important part, this chemistry, trace element chemistry. So this is getting to be an increasingly problem of complex data analysis. And so what we've been trying to do is kind of taking more advanced mathematical tools that are out there to kind of think about how we might analyze complex data sets. This is just an arbitrary data set, of sample number. I showed you 10 rows, it goes log, or ABCD are just elements, and the numbers are just parts per million. If you just look at that table, you can't tell just by looking at that data set if there's any relationship between any of these. But there are mathematical and graphical tools, artificial intelligence, which we are trying to try out to see if it helps us with this very challenging problem of country of origin determination. Just a few minutes about color. Color of any material is caused of three aspects or three components. You have the emission spectrum of the light source, you have the absorption spectrum of the object, and you have the color rendering capabilities of our eyes. If you change any one of these, the color changes. Now maybe you've gone to the mall in the afternoon to go shopping, eat dinner, dark outside, and you come out and you can't find your car. Well, the car has a change in color. Your eyes have changed a little bit, perhaps, in how they're sensing color, but the light source has changed, so you can't find your car. You've had that happen, Gary. Gary can vouch for that. But this is obviously, of course, the basis of the Alexandrite effect. You change the light source, you change the color. So spectroscopy is the way that we can analyze color, and these are some pictures. Robert Shigley Jr. was the son of our founder, Richard Liddicott, our former president, using a spectroscope to examine gemstones in 1938 on the left and late 1940s on the right. And what we're detecting is optical defects that are responsible for spectral features. So you're all familiar with the visible spectrum. Wavelength increases toward the red end of the spectrum. Energy increases toward the violet end of the spectrum. That's why you get a tan with UV light and not a hot lamp. Right, Gary? Thank you. You're very good at this. We present spectral data for visible spectra as a graph. So you see the wavelength, and I put in the color spectrum there for you, the color band. Absorption increases upward, transmission of light increases downward. So color in most all objects, certainly gemstones, I think almost all, I should say, I shouldn't say all, but almost all that I can think of is the result of selective absorption of incident light. So the white light comes into the gemstone, in this case this reddish-pink diamond, and I've listed all the higher parts of the spectrum are being absorbed by the gemstone, and the rest are not absorbed, and they're transmitted, and that is what your eye senses as the color. So these wavelengths are energies, and the defects in the material cause certain parts of the spectrum to be absorbed, and the rest transmitted. That's what causes color in most gems. Well, maybe I should go back to this. Oftentimes, you will perhaps notice that the horizontal axis has wavelength numbers, but the vertical axis has no numbers. Well, the numbers, the amount of absorption is related to the path length of the light through the stone or the material. So you have a greater thickness of material, greater absorption, darker color just by these darker boxes. I've been on a campaign for gems to be cut as flat plates. Unsuccessful, I would say. Flat discs like these glass or plastics. You have a known path length. You have a known amount. You can measure the absorption. You can put numbers on a vertical scale. Unfortunately, in gemstones, like this kind of example of a calculated light path through a diamond, the light bounces perhaps many times, and you have color zoning and everything. We don't know the path length. We cannot measure the path length, so we don't know the absorption. We can't measure it. Now, maybe you can do some kind of mathematical, kind of get an approximate indication But the challenge is we don't know the path length of light through the gemstones, so we oftentimes can't calculate the amount of absorption. My colleague Bob Cronishield was certainly, I think, one of the smartest gemologists I've ever known. I think Manu would agree there. I think a phenomenal individual. He was a great champion of the use of the spectroscope. And I think in the 1960s, he started hand-drawing the spectra with charcoal and pencil, hand-drawing the spectral patterns of the absorption lines in all the gemstones. I have all of his files, and I have some of these original hand-drawn spectrum patterns, and it's the basis of these color patterns that we produce in the Gemological course material today. Now, you all know about spectroscope. You can see you have the spectrum, the colors, you have broad bands, narrow bands, and you know the wavelength of the band. Now, I don't think the gemologists particularly care exactly what the wavelength of the band is. They're looking at the pattern of the lines, broad or narrow, because the pattern for a lot of gems is very distinctive. It's an immediate indication of what it is. And you can also see that some of the broad or narrow lines are very sharp edges, and some of them are diffuse. And that just means there's a large difference in absorption over a very narrow wavelength range or nanometer range. That means it makes it a sharp edge. If it's a gradual change in absorption, you get kind of a more diffuse band without sharp edges. Well, optical defects in gems produce this selective absorption or emission, fluorescence of light. So on the left, nitrogen and diamond, 3 nitrogens, a vacant carbon, missing carbon atom. That's the center that produces the cake yellow, light yellow color of diamonds. And on the right, you've got some chromium atoms substituting for aluminum atoms in the structure, and that produces the red color. So what we're chasing after in these visible spectra is an indication of these defects. So here again is my little example of white light going into a yellow diamond, and the diamond absorbs the blue and violet energies, wavelengths. The rest are transmitted and are recombined, and your eye sees the yellow color. And this is kind of how our graphical spectra compare with this spectroscope image. So the peaks on the graph correspond to the dark lines in the spectrum, and the peak height is kind of related to the intensity of the dark line. But why do we use an instrument called a spectrometer to record visible spectrum this way? A couple of reasons. Because of the detector, there's a wider wavelength range than what you can see with your eye in a spectroscope. We can detect very weak features in the spectrum, very weak peaks that you can't see with your eye. And you can have a very accurate determination of the wavelength, the nanometer positions of the absorption. Just kind of a little simple example for blue sapphires again. Main sources are metamorphic and magnetic rocks, and they kind of have some differences in their spectrum. And again, these differences in the spectrum reflect differences in the cause of the blue color. You all are expert gemologists, I know, out there. Probably quite familiar with polarizing filters and polarized light. A polarizing filter takes light that's vibrating in all directions and kind of constrains it to operate, vibrating in one plane. And when you have two polarizers parallel, they'll pass the light, and you put it in 90 degrees to run it, it absorbs the light. That's the secret. But the dichroscope or laryoscope can help you identify isotropic gems from anisotropic gems. The isotropic gems, the main ones that I can think of standing here, diamond, spinel, garnet. The light passes through them in any direction the same way. For other gem minerals, the light is going to be separated into polarized ways. It kind of perhaps take different paths. So just kind of as a little simple example, tourmaline, uniaxial, one optic axis, two refractive indices, So just kind of putting the polarizer filter into orientations, you see the pleiochroism. So if you want to understand cause of color, the ideal way is to create a sample that is oriented optically. And so ideally we're trying to produce a flat plate, known thickness, where you have the two refractive indices, the two optical directions in that plate. Tanzanite, we see a little tanzanite here to show a little more complicated, two optic axes, three refractive indices. In this case, you're going to need two flat plates to get all three refractive indices. But again, if you really want to understand coloration in gems, you need to kind of have some oriented samples to collect spectra. So we have a little optical orienting device shown here on the left. We take our rough sample, not your cut stone that you submitted to us, and you can glue it to a post, and you can move it around, and you can orient it optically. And then you can take it off the post and put it in a saw or in a polishing wheel, and you can polish a flat plate, or roughly flat plate. And this is an example. This on the right, you have a heated blue zircon with the two spectra, the bottom spectra where the polarizer is parallel to the optic axis. There's not much coloration, so the graph is flat. But if the polarizer is perpendicular to the optic axis, you get the significant absorption in the red end of the spectrum and you produce a blue color. So if you want to understand coloration in gems, the ideal situation is you can collect visible spectra from an oriented sample using a polarizer. Of course, we use infrared spectroscopy for many materials, example of jade, water, and emerald, polymers, and wax, and oils. A lot of treatment materials absorb in the infrared, and we can, again, we have kind of a reference database. You can kind of pretty quickly characterize, and this is also very important for detecting type 1 and type 2 diamonds. You can also characterize fluorescence. You're all familiar with a lot of D to Z diamonds fluorescing blue. So on the left, the fluorescence, this is a fluorescence intensity versus wavelength. In this case, we're illuminating the diamond with 365. That's the peak that goes off the scale on the left graph. And then you see the fluorescence emission in the blue region of the spectrum. So you fix the excitation wavelength and you scan through the emission. But you can reverse this and do the opposite. So you can set the detector, in this case about 440 nanometers, which is the high point of the emission, and you can scan the excitation, and you can get a very clear idea of exactly the UV wavelengths that are producing the fluorescence. Raman spectroscopy is very important for many things, but really one of the ways is really quite a fast way of distinguishing minerals based on the Raman spectra. I just show you kind of an example. It's rapid, non-destructive, using a laser. And because you have the laser oriented by the optics of a microscope, you can kind of analyze different parts of an inclusion, like a fluid inclusion. So this is just kind of a multi-phase inclusion in an emerald, and you can get a Raman spectrum of a calcite crystal, a salt crystal, a CO2 gas bubble, and a host emerald. This is when we were able to acquire this kind of technology. This is really a game changer for identifying inclusions inside gemstones that weren't exposed at the surface of the gemstone. We can also collect what's called photoluminescence spectra when we use different types of lasers, and this is particularly important for diamond. So again, it's fluorescence to laser light. We use different lasers to kind of sample different parts of the spectrum. And we can either hold a diamond at kind of a room temperature or a liquid nitrogen much lower temperature condition. We also have a way of taking a PL spectrum represented by the upper left, selecting a couple of peaks on that part of the spectrum surrounded by the red box, and move the detector and a pattern over the gemstone and detect that spectrum, that one feature, over that pattern of analytical analysis locations. So on the left, this is just an HGH grown diamond. You see the very classic diamond view fluorescence image. But on the right, you see this false color map of the intensity of this band, this PL band, at different locations in this diamond, or a similar type of diamond. And you see very clearly much the same PL spectrum pattern. It's amazing to me that you can look at defects at the atomic level and you can see where they are. This is a huge value, this mapping. We've kind of gone one step further a bit. We've kind of gone into, I would say, 3D photoluminescence mapping, or I guess the fancier word is hyperspectral imaging, but I don't know what that means exactly. So this is a little representation of kind of a spot analysis by different colored boxes, just representing different defects. So we can not only make an XY scan, but we can make an XY plus a vertical scan inside the stone. But my colleague also has built this instrument that allows us to collect spectra along a line. So what this is the spot moving along. But what we're doing now, we can collect these spectra across. And I think really almost for the first time, we can produce false color images. This is not fluorescence, but the different colors represent different defects at different depths, in this case within a diamond. And we can, for the first time, see where these defects are actually present. And it is, I think, an amazing step forward to be able to capture, again, atomic level defects and their distribution three-dimensionally within the gemstone. We've kind of been working with a scanning electron microscope, which is a kind of a very high magnification tool, up to maybe 40,000x. It produces an electron beam that's going to interact with the sample in different ways. But what you can image is surface topography, composition, growth structure. So the bottom two pictures of this diamond section, you get a topographic secondary electron image on the left and a cathodoluminescence growth pattern image on the right. We also use a technique called X-ray diffraction. X-rays were, I think, found in the early 1900s or the last decade of the 1890s. But they are the principal tool for characterizing or analyzing the crystal structure of minerals and gems. So you have an X-ray beam that comes in, an X-ray of known wavelength, and that is going to be reflected off of planes of atoms in the structure. And the planes of atoms are separated by a distance which is d. So in that little equation, you can measure the angle of the peak, as you see on the graph, the peak, the angle, and you know the wavelength, and you can calculate the d value, the d spacing. And from that, and you kind of are going to want to rotate the sample or powder it up, so you get many orientations, but you produce a list of d spacings, and what's important is you can calculate the size of the unit cell of the mineral. And this is one of the principal techniques. You're not telling about chemistry, you're talking about structure. And it's one of the principal ways that all new minerals are characterized today, and really for the past, almost the past century, based on X-ray diffraction data. We have a high temperature controlled atmosphere furnace, which again, I can't really get close to. But allows us to kind of heat treat stones under high temperatures in a mixture of gas configurations. This is just a little study that my colleagues reported on last summer, where we diffuse nickel into a synthetic spinel and produce this pretty profound sample color. So we do heat treatment experiments, diffusion experiments, which we never could do before, studying the effects of controlled heating on gem materials. One of my colleagues has been looking at isotopes, all Many elements have various isotopes which differ from one another in the number of neutrons. She's looking at oxygen-18. Oxygen, if you remember, is one of the most important elements on the Earth's crust. And you can analyze these isotopes by a technique that she understands, but I don't fully understand. But the point is, she's saying, and I think other labs have probably been looking at this as well, don't think I'm not saying that. But it offers another technique for characterizing, in this case, blue sapphires from localities around Mogok, which are going to differ slightly in their oxygen-18 values. We've also been kind of doing a little bit of radiocarbon dating on pearls and shells. Carbon-14 is a common element in many materials. These are natural saltwater pearls from an island off the coast of Venezuela. This island, I think, was one of the principal reasons why, after the discovery of this Columbus, who was drawing many Europeans to the Caribbean, so we were able to carbon date these to, you can see, 1450, 1650, 15, not too far removed from the Columbus time. We've also been looking at DNA analysis for pearl nacre or mantle tissue as a way of characterizing pearl mollusk species. So I think that this trend is only going to increase in using scientific techniques and instrumentation to study gems. In a combination with classical methods, I think it's taken gem testing to a whole new level. And you can see that in the journals today. But you must have proper data collection, interpretation procedures, calibration. These are quite essential for correct results. Gem identification should always be based on a variety of techniques. The most significant challenge that we face, and you will face, is the creation of a searchable information database on the kinds of stones you're testing, and the best data comes from gems of known origin. So I started this by saying, the research and the gem trade are kind of having kind of an increasing knowledge gap. I think there's actually coming together in two ways. One, I think, is a fairly good way, others a little more uncertain. The fairly good way is we have many lectures today available online from great gemological minds on various topics that you can learn from. The less kind of more challenging part of this is this. And I just show you some pictures I liberated from Google Images. Sorry. I don't say any names of any of these things. XRF for chemistry, Raman spectrometers, infrared. There are more and more of these handheld instruments developed by many industries outside our world for testing various materials. And you may think, based on a talk you recently heard, that you might buy one of these instruments for a couple $1,000s and test gemstones with it. This is not really the best smart idea. This XRF tester is probably a gold precious metals tester. You have a gold precious metals database in this little instrument. You do not have a blue sapphire database in this instrument. I'm just saying, if you are going to put your career, your reputation in this little handheld unit, I think you've got to be a little bit careful. So, before you purchase a device, I'm just giving you a little warning. Know how it works. Is it working correctly? What is it intended to do, and what do you want to do with it? Which are two different things, in many cases. Are there any restrictions or limitations on its use? How is it calibrated? If you don't know how to interpret the results, you can make some, significant errors, which I have done, of course, myself personally. Does it produce false results? It may or may not be useful for gem testing. And there's a lure of this. I can buy a little Raman unit, go around the show, point it at minerals, identify them. But you have to have a database in the instrument This is the most challenging part. So I would say, before you get carried away with little handheld gem testing in a little black box or something, be careful. Thank you so much. Now, Gary, since you canceled all the other talks today, you want to have questions? No. Emmanuel, no. Artificial and gemology? No, I can't. Emmanuel, one step at a time. Yes. Emmanuel is an expert. No. We've been studying factory-grown diamonds, lab-grown diamonds, since 30 years in quite detail. There is a huge amount of information published on this topic. Synthetic diamonds grow quickly in a lab or a factory or whatever. Natural diamonds grow over billions of years in the earth. You cannot create this geologic signature over 2 or 3 weeks of growth in the laboratory. You will never be able to create that. So, again, I think the idea is, what type of diamond? Is it a type 1 or type 2? Most everything that I see on the market is colorless material today. We used to see yellow, blue, all these. I don't see that so much anymore. It's almost all colorless. What is a colorless diamond? It's either a 1A or 2A diamond. So if you have an infrared unit, you can quickly tell 1A from 2A. If it's 1A diamond, I think it's probably 99%. You correct me, Emmanuel. You've always been correcting me. It's natural. But if it's a 2A diamond, it could be natural synthetic. So what do you do then? I think you must look at other features. I think fluorescence is a very powerful technique, because you have colors of fluorescence, which in many cases are kind of unusual in natural diamonds. You've got patterns of fluorescence, sometimes inclusions. But I think you kind of have to be familiar with all the literature that's been published on this topic and all the kind of keys, means of identification. I think another quite easy way is looking at strain pattern. When you put the diamond between cross-polarizing filters, now you know what cross-polarizing filters is based on a few minutes ago. Natural diamonds oftentimes have an anomalous, they're isotopic, so they should be black, but they have kind of an anomalous color, light pattern in them. Whereas synthetic diamonds, they're going in 2 ways, either in a uniform HPHD pressure vessel uniform. They have no strain pattern. There's no strain produced during the growth. And if it's a CV diamond, it's growing layer by layer, so you oftentimes see kind of a layered pattern in the polariscope. So just looking at strain pattern is quite important. But I'm trying to make a quick answer. There's a lot of information on the topic that you can find in the gemological literature. I can't see you. Are you standing there, Gary, in the light? Yes. The comments are short and the questions are long, or vice versa.
So, Jim, my question for you is, with miners who are digging this stuff up, what's the best piece of equipment for them to use to understand what they have that might be good, like in a rural setting, for them to really understand that this some of the basic science so they can get the best price?
What type of miners? diamonds or colored stones? Oh, colored stones. I think the best approach I would use is the ideas we conveyed in our little booklet training program. Bigger, cleaner, better color, more value. I think that's the simplest rule. If they just recognize those and separate those things out, I think that's the simplest answer. Anything else? I guess we should we finish up here, Gary? I mean, are these other people coming in? Or is... Okay, two more questions. Depends on the request. That's probably a good strategy. Well, I'd like to thank you so much for coming today, and anything we can assist you with. But thank you, Gary.